First of all, welcome to the third day of the Wide Bandgap conference. Today we are focusing on passives. At your point, it's mostly magnetics or magnetic materials. And so far we had SiC and GaN the last 2 days, and they ran quite well. We had a great cross discussion, and I'm very happy having this format chosen to get the crucial information to the engineers. We have, when we look to SiC and GaN, special requirements as these devices allow much higher switching frequencies than conventional silicon. And so it's now our discussion, what does the magnetic devices can improve to contribute and to match the higher switching frequencies? That's a general question I want to put into the arena to start a little bit cross discussion. And I see Lucas showed up. Welcome, Lucas.
Hi.
We are now, you heard my introduction words, Lucas?
Not actually. No.
No. I just talked a little bit in general that SiC and GaN request higher switching frequencies, and that need to be followed up by the passives, and especially by the magnetic components. And it's important to the reader and to the auditorium what they can expect and what they should look to. Your presentations had been pre-recorded and run, but now it will be good to start a little bit open discussions between the four of you.
Okay.
Eleazar.
Yes.
What's the most requested thing if you get in front of a customer who uses SiC or GaN?
Well, I was thinking about it, and I believe it depends on where the passives, in this case the magnetics, are used in the system. If it is a DC-DC converter, which uses, for example, GaN FETs for low voltage, let's say 48 volt down to 12 volts or down to 5 volt, we are seeing there switching frequencies which are actually under 1 megahertz. Can be 400 kilohertz, 500 kilohertz, 700 kilohertz, but below 1 megahertz. And higher switching frequencies, higher than 1 megahertz, that we see it mainly in very low voltage point of load DC-DC converters. For example, 5 volt to 3.3 or to 1.8 or 1.2 or 0.8. So to power the processors and the core processors, FPGAs, ASICs, and so on. So those point of load converters, yes, they switch at higher frequencies, megahertz range. We see magnetics. So we have MAPI, for example, which is targeting this, well, it's very, very suitable for these applications. And we know MAPI it's been used up to 5 megahertz in this case. Then for the, then we see also these inductors, which are type of chip 06, 03, or 805 packages, like PMCI, for example. They are also used in these very high frequency applications. Now for the other range, we have a broad range of inductors. And this is used for the DC-DC converters that we see for the low power side for GaN and low voltage. Now, when we see now SiC, so silicon carbide applications, high power, high voltage, then and we look at the gate driver, auxiliary supply, for example, then we see that the most important parameter we are receiving is request from the customer is the parasitic capacitance across the isolation barrier. So interwinding capacitance, and that's for the transformer. For the high power coils and magnetics, which are used, for example, in PFC stages, we do not have parts on that application. So we don't target that at the moment, but yeah, that's what we see at the moment. I mean, maybe Emil, you want to complete something there also?
Thank you, Eleazar. Yeah, basically you mentioned well. Yeah, so a bit of myself, I'm product manager at Würth Elektronik. I'm developing standard products. And of course, one of my interests is gate drive transformers. And when I say gate drive transformers, it's not the signal transformers. I think this starts to become old stuff, but it's the transformer that generates that small auxiliary isolated power supply that is needed by the IC gate drive controller. So for the gate drives, we have recently launched together with Eleazar a new series of transformers in a quite small package, EP7, with I would say low profile SMD with capabilities for surface mount applications, and as well for targeting low interwinding capacitance. So we have quite good common mode transient immunity, so it doesn't drag the system down. So it should not be, let's say, the weak point on the system. As for the topologies that we use here, we try to use, or we are using topologies that they don't need a feedback loop necessarily. So we want to avoid an optocoupler. So typically it's a direct access. I'm talking about, let's say, primary side flyback solutions, or even unregulated half bridge or push-pull or full bridge designs. And more recently, we work with Texas Instruments with based on their new IC development, UCC 25800. It's an LLC, small LLC. What is interesting on this one, because it's resonant, actually is getting used of the leakage inductance, which actually allow us to separate the windings and basically improve for even lower interwinding capacitance. So yeah, so for the gate drive perspective, I would say with this new series, we are pretty well covered. As well, we try to get also with some safety included. So the series that we talk about, it's online, or we talk about basic isolation according to two of the, I would say, most interesting standards that I'm aware of, 62368-1 and 61558. What I would like, because I also heard about high frequencies. Typically, for when we talk about high frequencies, I'm talking about this auxiliary supply switching, which probably can be in up to 200, from 200, 350 kilohertz in, let's say, in flyback, but even higher, even in megahertz range. But for the high power blocks, I think we are still talking about reasonable, much lower frequencies. The issue with silicon carbide and gallium nitride designs, I think, is about the ramping switch, so how fast they switch. And that's, I think, where comes the challenge, where it's still, let's say, 70 kilohertz switching frequency, but they switch so fast now that it may create disturbances. So common let's say displacement currents can be injected through the isolation barrier of the transformer because of this parasitic capacitance. So again, we want to have that capacitance as low as possible. I think that's what comes in my mind right now. Another thing that I need to add here is we are also looking at the bigger components, like for the PFC solutions, because as of today, in my mind, I see it's a PFC stage, which can handle, let's say, one phase input or three phase input, and they have different topologies there, Vienna rectifier, or I don't know, parallel, or whatever configurations are used. And then you have the stage where you have actually creating the isolation for the high power. It can be a full bridge design, or even there, we can talk about the resonance circuits like LLCs. Now for the PFC section, we are today working in a series of PFC that they will be soon launched, and they will be on toroid and in a flat wire. So that's what I can say as of now. Maybe I should not say too much about it because it's not released yet, but yeah, we are looking also at the options to get in the higher power level beside these small things around the big power supply. So
Thank you, Emil.
Welcome.
Who else? Donna, you want to add something to the?
Yeah, at the power supply manufacturers conferences for years, they've been asking to lower the losses, because the largest component on the board, now that people are trending towards surface mount components, the largest component on the board is typically the inductor. So what we've been trying to do is lower the losses, get lower loss materials, and so that you're able to use the higher frequency, which then with the time constant, you're allowed to go into a smaller size, faster switching. You require a smaller inductance in a power factor correction. So what we have done is we have come out with our cool mu high frequency and our edge materials, which will now support the lower losses that are required for these higher switching frequencies.
That sounds good. Thank you, Donna.
In addition to that, as in the presentation, the Frenetic presentation, what's interesting is that people are trying to simulate the designs. So what you need to work with is some simulation software, and Frenetic is providing that. And we are launching in December our new inductor design software tool, which will have our new materials in it as well for the toroids and the E-cores, allowing you to stack the cores, choose your wire, make sure the wires fit, and then plot the DC bias curve. Also, I'm always willing to send out samples if they're, under a certain amount of money. But, I find in engineering, when I first started in magnetics, even now with the designs, I made 5 designs, and I wound up 3 of them and they worked perfectly. And then the other 2, I had to do some adjustments on those 2 designs. So it took a little longer. And so what I find is the best way with a design is when a designer gets down to 1 or 2 cores, get the cores into the designer's hands and let him try it in his application. It's extremely hard to simulate a high current application. You know, you can simulate it, but it's very good to get the cores in your hands and actually put it into the unit. When I did the 22 kilowatt design, I can measure the losses with that number of turns, but I'm not able to drive those cores at that drive level to measure the exact amount. You need to have those cores into the circuit to be able to make those decisions.
Thank you, Donna. Lucas.
Yeah, to add something here, I also think, well, like Donna, we need to simulate our magnetics, and also coming back here to something that Emil said, and also Eleazar, which is parasitics. They play a major role in any converter, especially at high frequency, either if it is the leakage, the interwinding capacitance, interwinding capacitance. It depends on your application, but parasitics are one of the key roles there. We need to be able to simulate those. So that's, in my opinion, one of the key aspects when you want to deal with very, very high frequency, especially nowadays. High frequency sometimes means smaller components, because you can, for instance, if we talk about the LLC or CLLC, we can have a lower series inductance, so we can integrate it in the transformer. But one thing I have to say also is that when we talk about very high frequency, there is a loss. Even if we improve the materials, even if we get better cores, the losses are there, the components are smaller, we need to manage the heat. That's one of the key aspects I see for moving with higher and higher frequencies, which is how to manage the heat out of these smaller components.
Yes,
Yeah.
I would like also to add, thank you, Lucas. I agree with Lucas. And we'd like to add also one question. When we talk about high switching frequency, how high it is? Because for some engineers, 500 kilohertz is already high switching frequency. Or is it 3 megahertz? Or is it 10 megahertz? So we need to talk more in a quantitative way, and also look at what is the final application. If it is for a very low voltage, very low power point of load converter, it's not the same than it is if it is for a higher power converter. What we are doing right now in Würth Elektronik also is we are looking into materials for high switching frequency. Also doing some research there. But as said, it's very important to know what is not only to minimize as much as possible the core losses of the material, but also to know what the application really needs. Because we talk about wide bandgap, it's not just high switching frequency. I believe the most important advantage is lower switching losses, because they switch much faster. So the switching edges are, or the switching times, to say it better, are much shorter than for silicon devices. So even in a 500 kilohertz application, which might be considered by some as low frequency, you can start gaining points of efficiency with when you are using wide bandgap devices like silicon carbide or gallium nitride. So it is not necessary to only talk about megahertz range. Also in the lower frequency range, in the hundreds of kilohertz, there are also the benefits. And there are many magnetic materials at the moment who are performing very well there already.
Thank you, Eleazar. Is it right? Is Eleazar your first name and Falco your last, or otherwise?
It is correct. Eleazar is my first name, but I know that in Germany, Falco is a first name. So I get this question often.
It's a very popular name, so I thought, hey, let me ask. It's always good to have a learning curve. Okay. I think the auditorium hesitates to come up with questions, or the amount of engineers working on that know quite well what you are talking with them, that they are not coming up here. So we need to keep it between us, to educate the ones who are not coming up with questions, but they may gather good information by our cross discussions. And as you mentioned, the fast switching is also for EMI a problem. So you have to find ways that the fast switching is not a problem.
You're correct, Bodo. You're correct. So fast switching speed, for example, if we look at a hard switch DC-DC converter, let's say a buck converter, we look at the switch node. So mainly mostly square voltage waveform. And we compare the harmonic energy of this square waveform with different switching edges. So switching speeds, let's say, for example, 100 volt per nanosecond or 500 volt per nanosecond, and compare them, we see in the spectrum higher energy, so higher amplitude of the harmonics when you are switching faster. That means not only that, obviously the EMI emissions are going to increase, but that is also going to excitate all the parasitics that you have in your circuit. So resonance circuits, LCs, all parasitics also on the PCB, and that's gonna even generate more ringing that will not appear if you were switching slower. So that presents a challenge for the EMI filtering also. And you also need to look at what are the self-resonances of the passive components you are using in your filter, because as you have now you need to filter at higher frequencies, that also becomes a challenge. So you need to be very careful when selecting the components for your EMI filter for high switching speeds, so even higher switching speeds.
So magnetic design is a fine art of electronics, and all the people who only think that the semiconductors are the important parts, the magnetics, without them, the solutions will not run proper.
So
yeah, Donna, go ahead.
So now with the increase in the frequency and the increase in the EMI, and of course the regulations are tightening the EMI. So the magnetic manufacturers have gone with the powder cores. We have figured out how to make the powder cores at the 70 tons and 60 tons now in shapes. So traditionally, if you had a ferrite core and you needed to have the EMI suppression, you put the design into a pot core because you had the shielding of the pot core. Well, the designs in the powder cores now, we have the PQ cores, we have, the LP cores, we have the EP cores. And so those designs provide a lot more shielding than the standard toroid. So that's always an option if you need additional shielding with the core itself.
Donna, you have a really nice working place.
Thank you. That's my kitchen.
It's your kitchen.
It's my kitchen.
A very nice designed kitchen.
Thank you.
Let me ask another question. At the moment, you are located in the States?
Yes, I'm in Pittsburgh, Pennsylvania.
In Pittsburgh.
Yeah.
Pittsburgh is a wonderful town. I remember there was the ECCE a couple of years ago, and I took the railway up to them.
Yes.
This old railway which takes you from the side of the river up to an elevated area where my wife and I had dinner.
Mount Washington. There.
Mount Washington Railway.
Yes, very
Yes,
nice views from the restaurants at the top of the hill, looking down
Yeah.
on the three rivers and the city, basically.
Yeah, that's what I remember. So let's think what else we could bring up for education to the auditorium. Any good ideas in between the five of us? I'm looking to my backstage and they shaking their head. They had no questions come in. And I remember in real conferences, we had the same when I was at PCIM conferences, that no questions from the auditorium came up. But that's no big problem. We had a good chat between the five of us. And if you agree, we may go for the coffee break. And I say, thank you very much, lady and gentlemen, and looking forward to one of the next conferences to meet in person. APEC or PCIM could be the next one. And we are strongly working for next year to do the Wide Bandgap conference again in a real form as we did before. But Corona, we needed to make this decision because a lot of people international would not travel to come to Munich. And so we decided doing the virtual conference the way we did last year. And I'm quite happy that this works. And I hope you had fun if you look into other sessions. And so I can only wish you a Merry Christmas and a Happy New Year. And the last wish is to have peace on our globe. Thank you so much.